Welcome to the pre-recording of lecture 10 of MCS 572. So in this third part of the course, we start with shared memory parallel computing. So in a way we did this at the end of the first part, at the end of the first week, and I will, in some sense, this lecture is completely independent from what we have done before as well. So at the end of the first week, I illustrated multi-threading in Julia. So this is a high-level construct, and I will start with this as well. The main goal of this lecture is to introduce OpenMP, which is another standard, not to confuse with OpenMPI, so there's only one letter difference, but OpenMP is a tool to write parallel programs for shared memory parallel computers. Now, shared memory parallel computers, it's a long word, but actually every computer is a shared memory parallel computer. It has multiple cores. So on this lecture, it's still, even though this is a introduction to supercomputing, this is something that is done on a laptop. And the main point here is that we can go at very fine timescales. So the computations that we are doing here will take milliseconds. Okay, so let's get started. So what is our running example? So we will approximate pi again. So in the first week we did it in a naive way with Monte Carlo, and not so naive with the composite Simpson rule. So here I will be using the composite trapezoidal rule. So what is the trapezoidal rule? So with 2 points, if you can only take 2 function evaluations, then the integral will be approximated by the area of the trapezoidum with over base b minus a. So b minus a is the length of the interval, and the heights are the function values at the endpoints. This is not very accurate, but you can make it quite accurate by subdividing the interval. So here with n plus 1's function evaluations, you get a much more accurate approximation. And it is a simple rule. So everything is defined mathematically on this slide. So in the last lecture, I indicated decomposition methods for introducing parallelism. And here the integral over 0, 1, so the integration interval, is subdivided in 4 equal parts. And the schematic assumes that this is an ideal parallel computation. So what is now the difference with multi-threading? In multi-threading, the function is essentially shared by all the threads, but every thread has its own lower bound and upper bound for the integration interval, so the a and the b, and also has the sum for the approximation for the integral. So it's a much finer way to define parallelism. So just to make the difference with what we've done in the second part of the course, where we looked at distributed memory parallel computers, where we were essentially running a single program by multiple processors. And actually, every processor is identified with one process. So when we did this with Python, with the multiprocessing module, we were actually spawning many Python interpreters. So there's a huge difference between a process and a thread. A process can be seen as a separate program with its own variables, and it can do its own memory allocation. So in a way, writing distributed memory programs is actually kind of a very general tool to have parallelism, to introduce parallelism. The drawback, of course, is that there is communication overhead, and every process, even starting every process, takes time. So there's a lot of system time here, and typically we will only do distributed memory parallel programming when we have a computation that takes in the order of minutes. So with threads, we actually have many threads within a process. And all the threads, they share the same memory space, and also the global variables between the functions, between the routines. So it's a much finer way to address parallelism than multiprocessing. So it's separate also from multitasking. So in a later lecture, I will define multitasking, but this is multi-threading. Okay, how do we do multi-threading in Julia? So here is the composite trapezoidal rule in Julia. So we define this function. So we had the summation. In Julia, you have a very straightforward implementation. So you can see that we do n+1 function evaluations. We evaluate the summation in an explicit loop. Okay, that function will be executed in the following program. So this is an entire Julia program, which also includes the definition of the function on the previous slide. So what does this program do? It distributes the integration interval in as many pieces as there are threads. So at the very beginning, so nt equals a number of threads, it is going to run a parallel for loop. And we compute the bounds of the integration interval by subdividing the interval 0, 1 in as many equal parts as the number of threads. So the dx is the spacing of the subintervals. So, and every thread writes in the array sub-approx. So there is a shared memory sub-approx, which is initialized all to 0. So sub-approx, so the zeros functions here as a memory allocation. So the main process or the main thread in this process will allocate the space where every thread will write. So we did this in the first part of the course at the end of the first week. So this is high-level parallel programming. So there is this directive, the ampersand threads, and that will run a parallel for loop. So the trapezoidal rule is called with this function, but now with different number of bounds. So Julia takes care that all the local variables in the function, they stay local to the threads. So every thread has essentially its own copy of all the local variables that are sitting inside this function. So if you have to run something in parallel very quickly, so you have a sequential Julia program running, then there is little you should do to have this run in a multi-threaded fashion. Again, this is multi-threading, separate from multitasking. One can do multitasking also in Julia. But this is the first way to start, and it provides us somehow with a baseline. What I'm here actually indicating is that, so here is at the command prompt. So when we did this in the first week, I was using a Jupyter notebook with a kernel that was running 16 threads on a fast Windows laptop that had 8 cores and was supporting hyper-threading. So here I have a MacBook Air, which is not as powerful as that Windows laptop, but you can see that I can go from 1 to 2 threads and actually increase the accuracy. So every thread is still going to do 1 million function evaluations. So I'm actually totally doing 2 million function evaluations. And you can see that the composite trapezoidal rule is going to give me about 1 decimal place. So if I double the number of function evaluations, I get a more accurate. And I double twice, I go from 4 to 8 threads. So you can see the error is going down. So this is a quality up computation. So we are already working here with about 93 milliseconds with one thread. So it goes to 101 milliseconds on 2 threads, 106 milliseconds on 4 threads. And then I have about 10 decimal places accurate. So if I can wait 93 milliseconds on one thread, then if I can wait 106 milliseconds, I have a much better approximation. So to emphasize again the difference with multiprocessing. So with multiprocessing, it's highly unlikely that you can speed up something or can improve something that runs in milliseconds. Okay, so with 8 threads, if I wait 123 milliseconds, then I have have close to 11, more than 10 decimal places correct of pi. Okay, so this is our baseline. Can we do better? And of course, the answer is yes, we can do a magnitude better, but we need to think a little bit differently, and there is where OpenMP comes in. So I'm in the first introduction. So at this point in time, we're going to switch from Julia to C. So there are 3 official languages in this course, C, Python, and Julia. Unfortunately, Python has this interpreter lock. So the multi-threading module is very useful in Python for concurrency, but not so much for true multi-threading. And if you wonder again what is the difference between parallelism and concurrency, think about the polite dinner conversation. That's an example of concurrency. No parallelism there because it's a polite one. Okay, what is OpenMP? So OpenMP is for shared memory parallelism in languages, compiled languages such as C, C++, and Fortran. Also, Julia actually provides, and there are other languages that provide layers on top of OpenMP. So we have a working C or C++ program, and there are compiler directives that you add. A little bit similar what we did with Julia with these acrawl threads. So we can define parallel loops to this. So there are 3 things. So there are the compiler directives, there are the library routines. So when you apply the directives, you have to compile with a separate flag. And then there are environment variables. A bit similar to how we launched the Julia interpreter with this number of threads, specifying the number of threads. We can do this also with OpenMP with providing a directive. And there are, so OpenMP is a very extensive standard. So what we will do today is essentially improve that numerical integration example, but first explain what is the OpenMP and what is the multi-threading. So OpenMP works with parallel regions. So in one sequential program, you have here three regions, the A region, the B region, and the C region. And the blocks, essentially, they can be executed in parallel. So A1, A2, and A3 are instructions that can be executed in parallel. So the level of parallelism is so fine that we can think of even indeed instructions. But typically this could be a subroutine call. So we have now three parallel regions, and in a parallel region there are threads of execution that are started, and then at the end of the parallel region they are joined. So there is one main thread of execution, but then there are several threads of execution that are started in each parallel region. So here is when you run a crew of 4 threads, so simultaneously, so you have the parallel region with 4 threads, so there are the largest parallel region has 4 threads. So you see that thread number 0 takes the A1, B1, C1. Thread number 1 is A2, B2, C2. Thread 2, A3, B3. Then there is no more work for thread 2. And thread 3 is only active in the middle parallel region. So the language of threading is probably becomes now a little bit more clearly if you look at these red arrows. So you have threads of execution that run through this diagram. So there is also, so with MPI message passing, we had the manager worker paradigm. Here we actually have more the work crew model. So in a manager worker paradigm, we could still use threading like this. We could still have one master thread, and I will give an example of that, but typically one works with multi-threading in the crew model, a work crew model. Okay, let's get started now. So this is a hands-on course. So I have a hello world. So we have to C program. So we have a parallel region, the pragma open OMP. I should say from the start that C, so in some sense, if you are familiar with Python, then you kind of forced in this part of at least this lecture to kind of either choose between C and Julia. So learning C is a good effort as well. So C is a block structure. You have these curly braces that actually indicate one block of instructions. So you have the main program that is one block, but then there are two sub blocks. You have the master block. So this is where the master thread, so thread number 0 will say hello separately. And then all other threads will actually also say hello. So, but master thread will do something. So here you see the directives, the pragma OMP, and there is a parallel region that is declared with the hello world, so you can get the identification number of each threads. And the first instruction is that you can actually define at compile time, you can declare at compile time how many threads you would use. So I will indicate later that you can do this also at execution time. So there is the argc and the argv that can be used for that purpose. But this is our hello world. So here I was running this on a new, or not so new, it's already 2 years old, but an M1 MacBook Air. On Macs, so there is Brew, and entirely run by volunteers, and very qualified ones, I must say, but because it worked right away. Brew install libomp, and that will also have, so be a little bit careful which GMP that you are using. So you should then also be using the GCC that comes with Brew. So we compile with the flag -f OpenMP, and this is our first OpenMP program. You see that every thread, including thread 0, says hello, but thread 0 is kind of identified as the master thread, and that says hello. So you see that the execution is kind of a little bit strange. I did not change it, so I just copied and pasted what came on the terminal. You would expect that hello from the master thread would be the first instruction that comes out. But here it so happens that it is almost towards the end. Okay, so we are started. With many Linux installations, and actually I didn't try Windows on this one. On many Linux installations, there should be something. Also, the package manager should be able to install this OMP library. OMP being an abbreviation of OpenMP. Okay, so the next slides are detailing the specifications of the library routines. So we have the header file that will only be recognized if you have a compiler that that knows where to find the library routines. So after the installation of Brew, it gives you actually an indication of where to find the directives for the linker. So there is when you compile, there is also the include. So there are two folders. There is the include folder, and then there is the folder for the OMP library, the lib OMP. So these are the two instructions that we are used here. So at compile time, you can define how many threads that should be used. So that means that this kind of also gives you the upper bound on the speed up that can be obtained. Okay. So we are working with a crew or a team of threads. So every thread has a unique identification number. So based on that identification number, just like we did with the message passing, you can then define which instructions are executed by which thread. Okay, so the parallel construct will execute a number of statements in parallel. So this is the parallel region that is executed. So all the instructions are executed in parallel. And here the important point is that how this is done. So the scheduling of the threads. So if you have M statements and P threads, then the system will kind of figure out which statements to assign to which threads. So I mentioned instruction level. It's not that fine actually at the coding level, at the machine level. It's more the statement. So as a programmer, you can essentially also distribute statements with a very fine granularity. All right, so then the master construct. So you can, in this way, still think about the manager-worker paradigm. So here you have the master thread that takes the role of the manager. So within the team or the crew of threads, you have one thread 0, which is identified as the master thread. So we have the single construct. So you can say that I don't really care which thread executes this, but actually I want that one single thread does this, and who it is actually not really the master. So in some sense with the crew, there's actually not really that hierarchy. So we want any thread, any available thread that executes this. And the single means that this is kind of an instruction that could be very useful for a print statement. So you can indicate that with this single construct that for debugging purposes, for example, that you have entered that parallel region. So it also functions as a barrier. So here I ran this again, so the example in a single construct. So it so happened here that thread number 1 on my M1 MacBook with the brew installation of GCC and OpenMP had thread 1 that was saying hello. And then all the other threads were saying something. Okay, here is another useful thing. Sometimes you do not want to determine at compile time, but how many threads are being run, but you want to determine this at execution time when you launch it. And here this is another feature of C, and we encountered this earlier. So in every C program you can get the number of command line arguments, so you can actually check whether the user of the program specified any extra arguments, and you can get those arguments from the array of strings. This is, by the way, used in the MPI exec and the MPI environment to get the number of processors you want to be using. So here we can also use this with OpenMP. So our second modification of the hello world, and I'm now half hour in, and we haven't actually done all that much. But I'm getting out of the hello world. So here is how the program functions. If I want to use 4 threads, so that was that first, so it's now the second hello world. That will set the number of threads by taking the command line argument, the first command line argument, which is a string, and that will be converted to an integer. So here you see the setting of the number of threads. So the program is user-friendly if there are no command line arguments provided. So the default argument is the name of the program. You can also print that name of the program if you like, but here you see the start of the program. Okay, so in some sense, if you are not familiar with C, then I would strongly encourage that you take the opportunity to get familiar with C, because C is still a very efficient language. All right, so now let's get to, so I'm almost half hour in, I have 20 minutes left in this lecture, let's do something computational. So I have the trapezoidal rule, the composite trapezoidal rule. And this is the C definition. So remember the Julia definition. So actually the C function, C is seen as a lower level function, but the C code is not any longer than the Julia code. The point, however, being that Julia works with optional typing, whereas in C, you have to specify the type of everything. So here, when I pass function, I have to explicitly declare that this function takes in a double on input and it returns a double. So the A and the B are also doubles, and the number of function evaluations, or the number of subintervals here, is an integer. So inside the routine, inside the function, I also have to declare the type of everything. So that enforces some extra discipline, but the loops are actually also quite short. And if you remember the mathematical functions description, then this should be quite comprehensible. Okay, so this is our trapezoidal rule. Then there is a main function, there is an integrand. So this is a little bit pedantic here. I define my integrand in a function. So to define the square root of 1 minus x squared. So you see how the integrand is then being used within the trapezoidal rule. And this is the check on the program. So I was running this on the M1 MacBook Air. There is the time command on Linux. There is also the time command that you can run in a Mac. Looking at the manual pages, I kind of felt that the /user bin time was a little bit more convenient with the output. I did some formatting. So the real user sys, it all comes on one line. I separated this, assuming that here the real time is the wall clock time, 10 milliseconds, but the granularity, it doesn't appear that great. So on a Linux workstation, you would see the granularity up to 3 decimals after the dot. But it will do. So we know 10 milliseconds. And now I didn't actually give any optimization flags either. Oops. So that's still something. So I don't know what would happen if I would give the optimization flags. But note that Julia is oriented of high performance computing, but there I had 90 milliseconds. So here an unoptimized C program does this in 10 milliseconds. Now, you can argue, 10 milliseconds, how much better can this ever get? Well, it will get better. So let's do this. So multi-threading using OpenMP. And now again, I should perhaps, if I were a little bit more flexible, I should go to the ABC. So let me flip to the picture again. So I reorganized my slides a little bit. So let me go back to the beginning. So here, this picture, the ABC, these are actually the 3 variables that are local to each thread. So when I was trying to explain how the multi-threading worked with Julia, I was indicating that within the function there are many local variables. So in some sense I was saying it's not fair. I'm comparing 2 different models here. But how can you be better? Well, everything can be shared except the bounds of the integration interval and the number that you use to accumulate the sum. So only these three things need to be, and also there is the identification number. So here is what OpenMP allows me to do. So fast forward again. So I have my C program. I shouldn't use this arrow key. So I have my C program that took 10 milliseconds. So now I have my start of the program. So in some sense, I will not work with that function, but I will put the function inside the main program. So I will declare a parallel region, but now the private clause is indicating that every thread will have its own private I, A, B, and C. So the I is an integer, so that's the loop counter. The A and the B are the integration bounds. So the number of threads is set to 8. So here I declared the int p equals 8. In some sense, this is a transition, so you could use also the arc v with the a to I of arc v, the first argument there, and the 1 million could essentially also be provided as an extra parameter. So the 1 million is kind of the upper bound on what we are willing to use. So I could say that by then I have at least, so the composite trapezoidal rule here gives me more than 8 decimal places with 1 million function evaluations. In numerical analysis, so actually say that the prerequisite is numerical analysis. In numerical analysis, this is horrible. So we can do a lot better with extrapolation with Romberg integration. So but that is actually the wrong way of thinking here. Just an aside here. So I have the parallel region, and I have actually still the trapezoidal rule that I will call. But actually, what gets computed is that every thread computes its thread number. Based on the thread number, we know the integration interval. So I said wrongly that the I is the counter. No, it's not. So we have the lower and the upper bound in the integration interval. And the H is here the 1 over P, where P is the number of threads. So there is this private clause, and then there is the critical section. So in the critical section, every thread will update the current approximation for pi. Actually, it's pi over 4. So at the very end, at the when the parallel region has ended, it will be multiplied by 4. Okay, so the logic is still that we apply the trapezoidal rule, and we apply the trapezoidal rule with these private variables a, b, and c in this parallel region. Now, what is a critical section now? Here is an example from real life. Imagine a bank account that is shared by two people who each have their own debit card. Imagine a married couple. They both have a shared bank account. They have each their own debit card, and they want to withdraw money at the same time. So at the time when the withdrawal happens, the debit from and I suppose that this happens in an actual situation. So the debit will essentially serialize or sequentialize this simultaneous withdrawal of the amount of money. So if there is if there are insufficient funds to satisfy both withdrawals, then one of the two should have an error message. So I suppose that this is happening in a bank account. So you can also think about if you have multiple computers, you have your mailbox open and you start to make critical changes in your mailbox in one computer. You could do this at the same time by another person at the same computer. So you would think that you shouldn't have an inconsistency at your data. So the critical section actually protects this. It protects from that both threads actually have access to that shared variable. Okay, so that is essentially it. Let me dwell a little bit more on this. So I post the slides, and if you scroll through the slides, you can see the explanation. So here the clause private that you can extend to the parallel region. So that gives access different storage for every thread. The compiler is supposed to know how to do this, so the logic is still very nice. So we have these three separate of these four separate variables, and the types are actually declared in the C program. So the A, B, and the C are doubles. The int is an integer before the parallel region. Then there is the other construct, that's the critical. That indicates that there is another important region happening within the parallel region. Now here the critical should actually be a single instruction. So you will destroy all parallelism when in theory, you could also have an entire block of instructions there. But if you were to put the function called the trapezoidal in a critical section, then you would have no speed up at all. So it enforces inclusive access. So threads are blocked if they want to update the MyPy, and if there is another thread currently inside the critical section. Okay, so here is the running, and here is actually the punchline. So the punchline is that if you do time with 8 threads, look at the time, there is no difference. So it still happens in 10 seconds. I was executing this on a much more older MacBook Pro, Intel one, and there's 17 and 19 seconds. 19 seconds, yes, milliseconds, I'm sorry. So here the granularity is actually not good enough, so it still is within the 10 milliseconds. But I would expect that here the 10 could be also like 17 and 19 or 13 and 19. But still, the point is that you actually get a much better approximation of pi. So you have going from almost 2 decimal places that you gain by working with 8 threads. So this is an illustration of quality up at the level of milliseconds. It's also an incentive to still work with C, although later we will see multitasking with Julia. But here you see that with relatively modest changes to your C program, you actually get already a very good benefit. So I did not change the trapezoidal rule at all. So this is important. Okay, so this is the end, 45 minutes in. So OpenMP is open, so you can go to the website and there look at all the documentation. So this was kind of an hello world introduction. So the aim is kind of of this course to provide you an introduction, and in the hope that it's not too much overwhelming you if you look at what is available. But we can already write very useful multi-threaded programs. So in the hands-on supercomputing, you got access on a 44 core machine. So the second exercise here, working with 32 threads, should actually give you a realistic idea of what can be done. Also here, the 1 million may need to be increased. So you can also do an effort at the number of floating points, at the performance. How much performance do you get out of your processor if you look at, if you count the number of floating point instructions that are done by the composite trapezoidal rule. Okay, so this is the first of a sequence of lectures on multi-threading and multitasking. So in later lectures, I will explain what is multitasking, what is the workgroup model, also how to do this in Julia. And I will, along the way, also explain some other programming templates to make, with relatively simple effort, very performant programs.